How's it going, everyone? Welcome. Euler Gonzalez here, and today let's going to now explore about is the closure, what a closure is, which is something that we are quite familiar with. How do we get here to closures, especially in this functional programming course taught by Kyle Simpson. Shout out to Kyle Simpson, by the way. Shut up, man. Oh my God, Jesus. In this functional like JavaScript course, it is only to, as a JavaScript developer, see what is the benefit of using all of these kind of tools that we can add on into our tool belt. So by the time that we need to use it, we just only know what is the benefit of it. Why is this? Because this is quite similar to when you go out to a restaurant and you have to pay the bills, right? You don't need the mathematical proof of 2 plus 2 is equal 4, the addition, the subtraction, the division, multiplication. You just only use those because that gives you certainty that this will now give you the thing that you need to. In this case, is gonna give you is now the bill. It help you. It's gonna so people on that restaurant won't charge you more, right? So if you're able to use this tool, similar in the functional programming, we're gonna have our code that is provable. And not only that, because this is also part of the Kyle Simpson experience, and I agree with what he mentioned, because it's also that not only to make the code provable, which is great, but also for the reader of the code, that any time that it needs to use these particular tools, it knows that that won't affect the state of the program in an unexpected way. It won't cause side effects. So this is part of the value proposition of this, that the code is provable whenever you write this code, as long as you follow this set of rules, mathematical rules, you will have now the certainty that the code works as expected. And for the reader perspective is that it has now that certainty. So you can have the point of this is that the functional programming, especially function purity, which is something that we're going to discuss in today's video, is that now we can focus our attentions in stuff that actually we don't have that high level of confidence. In other words, wouldn't it be nice to have certain area of our code that we know that it will work, so it won't change because it's laid on the mathematical proof, right? So we can focus our attention on stuff that we don't have that level of confidence. So such as business logic, which is something that a lot of the time is changing, especially by policymakers. They change that like woman changing shoes. So this is the value proposition of this. Now, to understand that, or at least to reach to this part, which is the closure, because after that we want us to move on to the composition and then the immutability, and I think this will be a very, very important topic to look at, is that with this introduction of the functional programming, we need to understand the subtle difference between the functions and the procedures. So a function is something that it takes one input and returns always something. In JavaScript, anytime you create now a function, it will return always anything, even though that you don't define the return keyword explicitly. It returns undefined. So we look at what a function is, that not only that a function is to describe the semantic relationship between the inputs and the computed outputs, and also is to reduce the surface area of reassignment variables, which is, hey, if we want to have now certainty that this particular function won't cause any side effects or won't change the state of our application in an unexpected way, by reducing the reassignment surface, a lot of the time that will give us much more confidence than our code work as expected. However, there's certain scenarios that we need to run into some sort of these side effects, aka we changing the state of our application, such as talking to a database, do a network call, or read the DOM, a timestamp, or functions that returns different values. So for example, random, and ultimately anything that generates CPU hit as well as CPU time delay. So for those cases, all right, to make our functions pure, we want is to also, if not only that this function must return also something, but the relationship between the input and the output must exist, must be explicit also in our name, the function name. Additionally, that this function, we must reduce the surface area so we can prevent any of this reassignment or side effects that can happen. And that to make the functions pure, we want to map is the input with the same output. So given the same input, we have the same output. So when it comes to deal with impurity in our functions, so there are two techniques that we can go with. So one of them is at the lexical scope, or in other words, when you define at functions definitions, you can now take the lexical environment, all right, and copy and return a new state of that. And the other technique is that at function call, now you can take a snapshot of everything that this function needs and then restore the state afterwards. So this can be quite expensive, okay, especially in terms of memory, but you're going to evaluate when you can use this and so on and so forth. All right. And then we look at the argument adapters, okay. The TLDR of this is that functional programmers are obsessed with the shape of the function, pretty much of how you can fit like Lego pieces each other, all right? Or if you're moving out to a new department or a new rent, you want to, or if you are traveling, okay, to some new place, okay, you want to organize everything in your let's say your I really would like to move everything to your wallet. That'll be awesome. But you're going to structure your luggage in a way that you can now put all of this different stuff, your clothes, your pants, your shoes, and all this stuff that you need to carry on in a way that is now fit each other's. Like Lego blocks, like Tetris. So this is now part of the argument adapters, part of the way of how now functional programmer, when they call the function shape, all right, and how you can now fit all of these different shapes each one another, they call this as type signature. So it is important for a function to pass this stuff, and so the number of the stuff and the shape of the stuff is important of how you're going to pass it, as well as the order and the stuff that come out, or the number, the order, and the shape of the stuff that come out of this function. So this is the type signature in plain old English. Okay, so this is what we look, for example, at the unity and binary, and also some other arguments adapter like flip, all right, to actually match with another function shape. And this actually opens up a part of the library called Ramda to any time that you find yourself in working with any of this function in a very unusual way, or if you find yourself a new particularly pattern of how you can rearrange this function, instead of creating your own, you first look at what the community has, because that'll be much more intuitive because you're familiar with this shape. It's like, oh, you know what to do when you look at this kind of stuff. In contrast, when you see some of those custom stuff, it's like, whoa, 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 I don't know what this is, you know? Now, I think that this is the reason of why we're looking at this Ramda function, which is great, and also explore another topic that is also relevant to functions, okay? When it comes to describe the relationship, when you now want to call several functions and describe the relationship each other. And this is known as point free. So for those who are quite familiar with the 8th grade classes, a math class, when the teacher tells you to actually draw a line on a Cartesian, all right, on a graph, on a Cartesian graph, and when you fix the point at some level, all right, let's say if you fix the point on x equal 3, so you draw a line that is parallel to y-axis, or if you fix the point on 3, y3, so you draw a line parallel to, you can draw a line parallel to the axis. So in other words, you can draw a line by fixing the point. So the idea of this point 3, and I mentioned this because I'm gonna make the relationship later on, is that with the point 3 definition, where the idea is to describe the relationship of this function much more clearly without being explicit to define it is data points, it is inputs, okay? Now we can describe or see the relationship of all of these particular functions. This is when the readability can decrease a lot, but what you gain, and also that's why I will say that 99% of programmers actually want to be more explicit than implicit. But the value that we're getting here with these particular techniques of not being explicit about the data point that we need to pass to this function is that we are going to improve the readability by using is the equational reasoning, which is a fancy word that you can use with your colleagues or your team members to impress them. But this is just a fancy word to say is that if this function has the same, if this two function has the same shape, so they can fit each other, so now they are equal in shape. Therefore, you can now use them. So in other words, if you have a function that receives one argument and another function that returns one argument, so you can now is starting to compose those functions, which is something that we're going to see that later on, right? But with point free or this equational reasoning, equational in terms of shape, not in terms of value, now we can use them to define general and specific functions. But before going into that, because we're gonna see that another crucial tool in our tool belt is the closures. And a closure is just a way to remember, quote, quote, is variable outside of the functions whenever this function was called. So if you take a look at closure here, the closure, if you take a look at closure here, so closure is when a function, and this is something that is triggered by JavaScript when you return a function. So a closure is when a function remember the variable around, even around it, exactly, even when that function is executed elsewhere. So because closures per se is not functionally pure, we can make that. And the way of how you can make that, so for example here, is by now call that function, all right, anytime that we need to alter the state. So for example, in this case, this is part of the closure that we can use this, okay? So anytime, so we have now a counter. So increment function is closing over the variable counter. This is the way of how you can read this, okay? So yeah, you get this. You get this. The variable c is not a function purity in this case, and this is clearly because anytime that you now call a function, it's going to produce a new different outcome. So this is not function pure. However, how can we make that our function is pure, right? Well, by calling that function with the new argument, for example, like this, right? So unity is now a closure, a functional closure here. So we also look at a particular example that to me was quite interesting to use because that opens up now the ability to play with function definition and function execution. And any time that, which is something that I actually put here, okay, if you're going to use a closure in a functional programming, you have to make sure that you're closing over non-mutating values. So for example, like this, all right, if you're gonna close over to something in a pure way, make sure that those variables are not mutating that. So what happened when perhaps you need to mutate that, or that another important concept of closure or a function is that when those functions are executed eagerly or lazily, right? So perhaps you want or you need is to say, hey, I want that these functions, when I call it, I want to execute these instructions. So for example, like this, all right? So when I call this function again, so now I have this computation already catch that. Okay, somehow already catch that. But sometimes you say, no, I don't want to do that because I'm not sure when this computation will run. So therefore, I want now is do that lazily. All right. So by the time that you call now A in this case, you are now executing that lazily. When you need to do this, it depends on your scenario, it depends on your use case, and why are we using this, or why do we even care about function execution order, right? Because it's all gonna depend of when you need to call these functions to compute something. So sometimes you want to do that early, or you want to have much more control by triggering that lazily. So this is something that when you for some reason wants to catch your result, wouldn't be nice to have some sort of way to do that? So for example, let's say you now compute this, but if you already compute that data, well, you don't need to recompute it. You just want to have access to that data. And this is where now memoization techniques comes here. So memoization is just a technique for, which is something that is using behind the scenes React and all the kind of frameworks. Yeah, frameworks like React is using that. This memoization, which is the way of how you can now is catch a computed value. So if you already compute that value, so you don't need to do that. You just only access to that result, and so on and so forth. This is just a silly example of how you can do in this case of the repeater, right? So the problem with this approach is that memoization per se like this, despite that it looks like, or despite that it's not looking or it's not obvious for the reader to be a function pure, okay, it is a function pure. So that's why we can use, for example, is now a memoize function for that, where this is something that can come from a particularly Lambda library. That the whole idea here is that it's going to close over variables and catch them when you need to compute them, and only and catch the result when you need to compute them. And then, okay, now we're going to talk about another concept here, which is called referential transparency. This is referential transparency. Okay. So referential transparency. Okay. Let's get into this. And the referential transparency and generalized to a specialized function, and generalized to a specialized function, to a specialized function. And things like partial application, incurring, and partial application incurring example, and changing function shape with curring. Okay, makes a lot of sense. Okay, so yeah, let's get into this. Partial application incurring. So partial application incurring. And then we have now is the partial application incurring exercise, right? Oh, partial application incurring comparison. So partial application incurring, comparison. All right, let's get into this.
It's a choice of where we put the code to decide whether we want it to happen eagerly. We're finally ready to get the final answer, for at least for the purposes of this course, to what is a pure function. Okay? Let's review where we've been so far. We started with a pure function needs to take some inputs and return an output. That's where we started at the very, very beginning. Okay? That was good, but not good enough. And then we said, well, no, actually, it needs to have a relationship between the inputs and the outputs, which was better, but still not good enough. And then we said, well, no, actually, they need to be direct inputs and direct outputs, which was good, but not good enough. And then we said, well, no, actually, they don't have to be direct inputs. They can be indirect as long as they're not changing. Remember, we can close over stuff as long as it's not changing, which was even better definition, but still not good enough. And then we said, well, actually, the real thing is it's the function call that every time I call the function with the same inputs, I should get the same output. If that's true, then I have a pure function call, right? Even better definition, but still not complete. Here's the full canonical complete definition for.
So we went over the several functions rules to the several functions rule to understand function purity. So initially we say, hey, a function must return something. Great, but not good enough, you know?
The very, very beginning, okay? That was good, but not good enough.
Exactly. Great, but not good enough.
A pure function needs to take some inputs and return an output.
So a pure function must take some inputs and return some output, right?
That's where we started at the very, very beginning, okay? That was good, but not good enough. And then we said, well, no, actually, it needs to have a relationship between the inputs and the output.
So a pure function must have a relationship with the input and the computed output, or the output.
Which was better, but still not good enough. And then we said, well, no, actually, they need to be direct inputs and direct outputs.
Yeah. So a pure function must have direct inputs and direct outputs, right? And I'm going to highlight, and I'm going to highlight this. Okay.
Which was good, but not good enough. And then we said, well, no, actually, they don't have to be direct inputs. They can be indirect as long as they're not changing.
So a pure function can have indirect input as long as they don't change. As long as they don't change.
Remember, we can close over stuff as long as it's not changing, which was even better definition.
So for example, with closures.
Definition, but still not good enough. And then we said, well, actually, the real thing is it's the function call that every time I call the function with the same inputs, I should get the same output. If that's true, then I have a pure function call.
So a pure function when I call it, I must get is the same output given the same input. Okay, same output, same input, right? But here's the canonical.
Right. Even better definition, but still not complete. Here's the full canonical complete definition for a pure function. And specific.
Canonical. So here is the canonical. Okay, here's the canonical complete full definition.
Specifically for a pure function call. Remember,
Here's the canonical complete full definition for a pure functional function call, because it's all about this. Full definition for a pure function call.
we're focused on the function call. Line 9 is a pure function call because, or if, I could take the return value of that function call and replace the function call with the return. In other words, if A was somehow being used somewhere in the program, like it was part of some other expression, which always returns the string, if I could take the string A, and literally just replace the function call with that value. If I could do that and not affect any of the rest of the program, then I have a pure function call. There's a very special term. Again, if you say this to your coworkers after the course, you're going to sound much smarter. So use it. Use it with your boss. Okay? The term is called referential transparency. Sounds cool to say, doesn't it? A function call is pure if it has referential transparency. Referential transparency means a function call can be replaced with its return value and not affect any of the rest of the program.
A function call is pure. Make sure to put this. So a function call is pure when the output, when you can replace the
Referential
output.
transparency. Referential transparency means a function call can be replaced with its return value and not affect any of the rest of the program. Referential transparency. Referential transparency means a function call can be replaced with its return value.
A function call is pure when you can replace the returned value
and not affect any of the rest. If it has referential transparency. Referential transparency means a function call can be replaced with its return value.
A function can be replaced with its return value. A function call is pure when you can replace the return value
and not affect
this
Referential transparency means a function call can be replaced with its return value and not affect any of the rest of the program.
And not affect any of the rest of the program. Here's the canonical here. This is known as referential transparency. Yeah, this is known as referential transparency. And referential transparency is just a fancy way to say, hey, a function pure is, a function call is pure when you can replace the returned value and not affect the rest of the program.
Transparency means a function call can be replaced with its return value.
A function call is pure when you can replace the returned value
and not affect any of the rest of it.
When you can replace the returned value.
It turns out referential transparency, that's a really key idea. It turns out that in a language like, for example, Haskell.
Why are you doing that? Chill.
The granddaddy of functional programming. Now, it turns out referential transparency, that's a really key idea. It turns out that in a language like, for example, Haskell, like the granddaddy of functional programming, referential transparency is a key characteristic of the language and of the compiler, indeed. Because in Haskell, when you write functions, they're always pure, which means they always have referential transparency, which means that because that's a guarantee of the language, the compiler can take advantage of that. It literally like memoizes everything because it can do that for free. it can literally replace other function calls with the inline result of the previous function call. They do that automatically for free because they have that guarantee of the language. We do not have that in JavaScript. Okay? So does referential transparency only matter if the compiler can do it? Some would say yes, but I would say no. In a bigger sense, the real benefit of referential transparency is actually to the reader of the code. Consider any function call in a program that is in
Why are you doing that?
need a pure function call.
So the benefit of referential transparency is actually for the reader of the code. Because you can have now is the certainty that when you call this function, not only that you can replace this value, so when you call this function, you can replace this return value and not affect the rest of the application.
The reader of your code reads line 11, and they go and they compute it, and they say, okay, I know that line 11 is this value, the value 42 or whatever. Everywhere else that they see that exact same function call anywhere later in the program with the same inputs, do they need to go recompute the result? No. Because what are they going to do? They're going to referentially swap out the function call for the result they've already computed in their head. And what's that going to do? It's going to free up their brain power to focus on other more important parts of your app. So referential transparency, while it matters a lot to the compiler in something like Haskell, for us in JavaScript, the reason it matters is because it puts the responsibility on you, the author of the code, to make it as easy as possible for the reader of your code, which includes your future self, to be able to look at a line and know exactly what it's going to do.
So the benefit of referential transparency is actually to the reader of the code. Because when you... The benefit of referential transparency is actually for the reader of the code. Because when you do... because when you do this, because it puts the responsibility on the author, on the code's author, which can be your future self. Okay, because it puts the responsibility on the code's author, which can be your future self. Okay, exactly, because it puts the responsibility on the code's author, which can be your future self, that anytime you see line 9, you don't have to recompute mentally that, since you know what it is. So this is the benefits of functional programming. Again, like any tool, it has its trade-offs. All right?
And then not have to redo that.
Because at some point we need to actually manage its state. We need to change the state or try to keep track of the state change.
Work over and over and over again.
That's what we're going to see that later is now immutability. This data structure that allows to keep track, or that has now mechanism to keep track of state change. Holy moly, bro.
Said at the outset of this course, the best code is the code that didn't have to be read in the first place.
So the best code is the code that you didn't need to read about it.
And then not have to redo that work over and over and over again. I said at the outset of this course, the best code is the code that didn't have to be read in the first place.
Didn't have to be read. Didn't have to be read. So the best code is the code that you didn't have to read.
Because I looked at it and said, oh, I've already done that. I don't need to do that. That's why function purity matters so much. It's like we're building up this pyramid, and this is the base stone of the pyramid. And if you take it out, everything else would crumble. You cannot have anything else in functional programming unless you get the value and the importance of function purity. Function call purity specifically. We talked a bit earlier in the course about this idea of...
That makes a lot of sense. Again, like any tool, it has its trade-off. Let me make a quick pause, and let's keep going. All right. So now that we know what is referential transparency, is all about, which is just a fancy way to say that, hey, anytime that I call this function, anytime that I call this function, and if I can replace its return output, and it won't affect the rest of the application, then this function is now pure. It's a referential transparency, right? So a function call, because it's all about the function call, so a function call is pure when you can replace the returned value and not affect the rest of the application. This is referential transparency. So let's go with the generalized to specialized, right? And partial application and curing and all that kind of stuff. All right.
Of function specialization, we briefly glimpsed it, and I mentioned things like partial application and currying. We're going to come back and dig into that fully. So that's what we're going to talk about. The idea of going from more generalized functions to more specialized functions. This is a key concept in functional programming.
Yeah, absolutely. This is a key concept of from more generalized to specialized. This is a key concept from functional programming, and I know because there is a lot of value from it. And value is that practicality, the stuff that you can actually act upon that. So
that's what we're going to talk about. The idea of going from more generalized functions to more specialized functions.
So the idea to go from more generalized functions to more specialized. A key concept or a key idea in functional programming, right? There you go.
This is a key concept in functional programming. All right, so let's imagine I have a function called Ajax. It takes 3 inputs, a URL, some sort of data parameter, and then a callback. And I might call it like you see on line 3, which is I call it with some variable called customer API, pass it a data object with ID 42, and then I pass it a callback that's going to render that customer to the screen, for example. Now, there's nothing wrong with line 3. It does get the job done, and you've probably written code like that on many occasions in your applications. But what I want to point out is that that line has a lot of detail in it that may not be necessary for the reader to see at that exact moment. And that's really, it's not just that we want to make the line shorter or make it longer or something, but we really want every line of code to have only the amount of information, no more, no less, that the reader needs to see at that point. So let's consider some intermediary steps which might allow the reader to understand things a little bit more clearly without having to read through a long line of a bunch of different data.
Code
so one thing I could do is I could make an intermediary function called getCustomer. Now getCustomer already knows that it's going to make all of its Ajax calls against customer API, and it only intermediary function allows the reader only the amount of information, no more.
Or only the exact. It contains the bare minimum, but it contains only the
or no less that the reader needs to see. The line shorter or make it longer or something, but we really want every line of code to
every line of code to only have the amount of information.
Have only the amount of information, no more, no less, that the reader needs to see at that point.
So the idea is that every line of code only contains. So the idea is that every line of code only contains the needed information, no more or less. So the reader of the code knows the intent. Know the intent. What is the intention here, and the another here, and the another here, and the another here? Is that to understand
that point. So let's consider some intermediary steps which might allow the reader to understand things a little bit more clearly without having to read through a long line of a bunch of different data. So one thing I could do is I could make an intermediary function called getCustomer. Now getCustomer already knows that it's going to make all of its AJAX calls against customer API, and it only needs to receive data and callbacks, but it doesn't need to receive a URL because that's sort of hard-coded. Okay? Now on line 9, I'm calling getCustomer, and I'm providing that same object with the ID 42 and that same render customer. So compare line 3 and line 9 in your mind. Which one of those two lines is more clearly describing to the reader of the code what the purpose and intent of that line of code is? And I think most of you would say line 9. It has a semantic function name there, which is better than this general function named AJAX with a customer API. It describes something more clearly. So making that function may not ever be called more than once. You know, you're used to, we talked about this dry thing, you're used to thinking about, well, I only make something into a function if I'm going to call it 3 or 5 or 10 times. I think Uncle Bob said, you know, only make it into a function when you've copied it the 3rd time or whatever. But I'm here to tell you that one of the reasons why you make something into a function is so that the code is more semantic. The name of a function call describes its purpose, and purpose is the key thing that we want to communicate to our readers. So,
So the purpose is what we want to communicate to the reader. So in this case, okay, even though that you have now AJAX, all right, and similar to this, get customers. So you are now, okay, so in this case, which one of the line, so in this case, which line is more readable? Line 3 or 9?
Even if I never was going to call it ever again, there still might be benefit to defining getCustomer so that I have a more clear name for what's happening on line 9. And if that's true, then we can extend that even further. Because there might be places in our code where we need to get customers, but there might be other places in the code where we need to get a very specific customer, like, for example, the currently logged in customer. So we might define a further specialization function called getCurrentUser. And getCurrentUser is hard-coded to the ID of the currently logged in session or whatever. And all it needs is a callback. So line 16 compared to line 9, and therefore compared also to line 3. Comparing those 3 lines of code, can we see that line 16, for the places where that would be what we wanted, line 16 is even more semantically self-descriptive than is line 9, which itself was more descriptive than line 3.
The current user.
We haven't changed any of the functionality here. That's a key component to understand. We have not changed the functionality. We have simply changed the stylization of this code to be more semantic. Now, defining getCustomer manually the way I did, and then defining getCurrentUser manually the way that I did, that's a bit of extra overhead work. And you might say, it's unfortunate that I have to do that definition of a function just so that I can get a nice clean function call on the call signature. Oh, by the way, line 12, I've commented that line out because line 13 defines getCurrentUser in terms of getCustomer. But I could have defined getCurrentUser in terms of just the AJAX call. Would have had the exact same outcome. Can anybody tell me why we might choose line 13 over line 12?
the give me a pause here. I'll be there. All right, let's go.
It's more declarative.
It is more declarative, but more specifically than that, it creates a clearer relationship.
So the relationship.
It says get current user is the specialization of get customer, as opposed to saying
between get customer and get current user. It creates a clear relationship between get customer and get current user. A more generalized function. Yeah, a more generalized to a specific. To a more generalized, or from, because of that, from a more generalized to a specific, to a specialized function, to a specialized function.
it is the specialization of Ajax. Saying it's the specialization of Ajax is a weaker statement, relationally, than saying it is the specialization of get customer. So even though both might have the same outcome, the choice of line 13 makes a clearer, more obvious signal about the relationships between these entities. Yes?
All I was just saying is that current user also kind of implies that it is a customer.
Yes. Yeah, I mean, basically, I could have called it get current customer or whatever. But yes, basically, right? So in our domain model, that would be obvious to the reader, right? But defining these functions manually certainly has the downside, which is that we're cluttering up this code. You might have to take those and put them somewhere else or whatever. So is there some way that we could define these more specialized versions of functions, but without having to define manually pointed functions like this? These are pointed definitions rather than point-free. How could we define them more clearly? First thing you need to understand before we move into that solution is, as I said earlier, the parameter order matters greatly. When you're going to specialize a function, that is an array function that takes...
Interesting. Function parameter order matters a lot.
It's 3, 4, 5, 10, 20, whatever inputs. The order of those inputs matters, and basically, the order should always be from the most general of the parameter on the left to the most specific of the parameter. Because we're going to provide those inputs one at a time, the way we were doing manually, and you want to unfold them in that order. If you had the most specific one on the left, well, now it's going to be harder to provide that input because you're trying to provide a more general input first, and you're having to skip over a more specific input. So it's important when we design our functions to design them so that their parameter orders are going from general to specific. By the way, you will encounter this in your functional libraries when you're exploring something like Ramda or whatever. For example, the map function. Most of us, I think, are used to thinking in terms of a utility like map, which takes 2 inputs, we're used to thinking, okay, I'll pass the array as the first input, and I'll pass the function as the second input. But you'll notice that every functional library in existence will do that reversed. It will pass the function first, and then it will pass the array. You may never have stopped to wonder, why is it that they do that? They do that very specifically because the array values, the data, is the most specific of all of the inputs that could possibly go in. And then the callback is more general of an input. So if we're going to specialize a map call, we're almost always going to provide a mapper function and then provide new pieces of data, rather than provide a single array and provide different mapper functions. You with me? So parameter order does matter when we shape these things. And sometimes the parameters are correct in the right order. Sometimes we have to juggle them with those utilities like flip and stuff. In terms of our Ajax function, there are 2 techniques for how we could specialize it. One of those techniques is called partial application.
So they are okay. In terms of specialized functions, there are 2 techniques similar with the function purity, when we have 2 techniques of how to do this kind of stuff to make the code provable, to make those functions that work as expected, to make the code provable. Okay, is that by extracting the impurity is like, hey, you can is by the function definition take the lexical scope and pass it, or a function call, you're going to now take a snapshot of everything and then restore the state afterwards.
So let's look at partial application. Here's my Ajax function, line 1. Line 3, I am making a partial application of the Ajax function, and that result is getCustomer. And the way that I have made getCustomer out of Ajax is by pre-specifying the customer API URL as its first input. So envision a utility called partial, which I'm not going to show the implementation of because it doesn't really matter how it's implemented, but it's provided to you by all the functional libraries. It takes a function as its first input, and then it takes as its next inputs a set of arguments to pass along to that function at some point. So it's like presetting those arguments.
Is a function.
And we get back a new function called getCustomer.
Values.
I can take line 4, another partial of Ajax, and provide it 2 inputs and get me a getCurrentUser. But line 5 is better than line 4 for the exact same reason as we just talked about. Line 5 makes a more clear delineation of the relationship between getCurrentUser and getCustomer. That is, getCurrentUser is a partial application of getCustomer. So that partial utility allows me, each time I call it, to preset 1 or more inputs and produce a function which is expecting all the rest of the inputs. That's what partial application is. Partially applying some of the inputs now, receiving all of the inputs later. You'll notice that to do a 2-stage specialization like I did, I had to call partial twice. You see that? I had to call partial once, and then I called it a second time to make the getCurrentUser.
And then apply that later, and then the rest later.
That's one way of doing specialization, is called partial application. Another way, which quite frankly is much more common within functional programming, you will tend to want to do partial application as you get started, and then you'll find out actually everybody does currying. Okay? And you'll see why as you go along, as we go along in the course and as you get more practice with this. But currying is the much more common form of specialization. I used to tell people, and many people have said this before, I used to tell people that currying was a special form of partial application. I now would describe them more like cousins. They both accomplish the same end goal. They both specialize a generalized function, but they go about it in a somewhat significantly different way. So let's look at currying. Back to our Ajax function. What if I wrote the Ajax function like this? Okay? It looks a little bit different because I have this 3 levels here. I have an Ajax level, and then a getData level, and then a getCallback level. So I've got 3 levels of function going on. And notice line 7, when I call it, I'm actually calling I'm doing a first set of parentheses line 7 for the customer API. That provides the URL. And I get back another function which is expecting the next input, and then I get back another function which is expecting the next input.
This is
See
a
where
function
where I'm going here?
definition.
So I've got 3 functions nested, and then I've got 3 function calls. That's what I would sort of refer to as a manual currying. Okay? And you'll sometimes see people define, if they just have a 2 or maybe a 3-level currying, you'll see them list out the functions nested like that. On the next slide, we'll see an alternate way of writing out a manual currying. But that allows me then to call those functions and save off the intermediate function. That's how we get the specialization. If I call Ajax with only customer API, I get back a function which could be called getCustomer. The function on line 2 is essentially getCustomer. Use your equational reasoning, and you'll see that they're basically the same thing. Exactly. And then if I call the getCustomer
so with the equational reasoning, is like with the getCustomer, you actually now have is this, and then you're gonna pass is the, because you now is getting a more specialized function like this.
Data, what I get back is get current user. So you'll see the same specialization just as we were doing on the previous slide, but now notice that I didn't have to call like a utility every line. All I had to do to get the more specialized function was just pass in the next input. Pass in an input, get a more specialized function. Pass in another input, get an even more specialized function. And you keep doing that, you keep getting a more specialized function every time. This is a technique called currying. Where does that come from, by the way? The Haskell programming language. Everybody knows or probably has heard at some point or another about Haskell. I don't really know anything at all about Haskell. I can literally write 1 line of Haskell. That's all I know about the programming language Haskell. But what I know is that one of the co-inventors of Haskell, his name was Haskell Curry. He invented this technique of currying, or at least co-invented this technique of currying.
Haskell Curry, and that makes a lot of sense. Holy moly. Curry's paradox. So he invented this technique. Holy moly, Haskell Curry. Haskell Curry.
We call it currying because it is essentially the way that all inputs go into functions in Haskell. So in Haskell, you don't write like a binary or an n-ary function. There's no such thing. All functions are unary in Haskell. So if you want to pass in 3 inputs, what do? You have a currying function that takes them one at a time. There's no such thing as pass all 3 all at once kind of thing. So currying comes from this idea of, if I could only pass in 1 input at a time, how could I make multiple inputs go into a function? Sometimes my function needs multiple inputs. Now, This is doing it manually, but it would be nice if, for example, we had a utility that could do that for us. And indeed, we do have a utility that can do that for us. By the way, in the commented lines, you'll notice that I'm using the arrow function syntax. Line 1 is the traditional way that that is written out. And that you'll see URL and then the fat arrow. Let me highlight this for you. You'll see URL here. My highlighter will ever work. There we go. URL, and then the arrow, and then data, and then an arrow, and then CB, and then an arrow, and then whatever the function needs to do.
So this is the way of how you can actually pass input.
That's that 3-level nesting. It's just written all in one line. And a lot of functional programmers really like the arrow function syntax because this arrow function syntax is almost identical to the mathematical notation and the Haskell notation for a curried function. That's why they love writing it in that style. I am decidedly not a fan of arrow function syntax, which is why you haven't seen any arrow functions on any of my slides. I'm not a fan of that syntax, but if you absolutely must do this chained arrow currying thing, please do line 2. Do a favor to the reader and at least wrap parentheses around each function boundary. Just slightly more not so crazy on the readability, okay? If I can't convince you not to do nested arrow functions, please at least wrap your arrow functions in parentheses, your nested arrow functions in parentheses. Okay, arrow functions aside, in JavaScript, we can define a utility, and indeed, all functional libraries will provide you a utility. It's often called curry. Sometimes they'll have a variation of it called curry n, meaning like how many I want to curry. It looks like this. You call curry, you tell it how many inputs you're expecting to receive, and then you provide it a function. And notice that this function here doesn't have to be manually curried. It's a regular old normal function that's expecting some n number of inputs. This curry utility automatically adapts it into being that unrolled thing that's going to accept one input at a time. In other words, it creates a wrapper adapted function whose job is to keep returning a new function that expects another input until you've provided the specified number of inputs, and then it calls the underlying function with all those collected inputs. And that gives us the ability, line 7, to call AJAX with the URL and get back a getCustomer function, and then call getCustomer with the data object and get back a getCurrentUser function. So you'll notice that we have the same outcome with curry as we had with the partial application. We just got there in a decidedly different way. Same outcome, which is that I have a general function AJAX, an intermediately more specific function called getCustomer, and an even more specific getCurrentUser. But with partial application, if you were to look a couple slides back, to get each level of the specialization, I had to call the utility again. With currying, I call it once at the beginning to set up my function, and then it automatically specializes itself as I pass inputs. And I think that's one of the reasons why currying is more attractive, is it ends up being that you write fewer calls to these utilities. You call it once to set up a function, and then you just automatically can specialize it. As a matter of fact, virtually all functional programming libraries that you will encounter, all of the methods on those functional libraries are automatically already curried. Because it turns out functional programmers want everything to be curried. And if you remember what I said at the very beginning when we were talking about shapes, one of the reasons why functional programmers like curried functions is because they like unary functions. Single input, another output. And you can see that a curried function is exactly that. It is a chained series of unary functions. Single input, single output, single input, single output, single input, single output. So in other words, to summarize this partial application versus currying thing, what we could say is that they are accomplishing the same thing, but doing it in a different way. Both of them are specialization techniques. Partial application is going to preset some of the arguments at the beginning, and then receive all the rest of them on the next call. Exactly. And if you want to do multiple steps of that specialization, you've got to keep calling the utility. Currying, on the other hand, doesn't preset any of the arguments, and it receives each argument one at a time. If you ever get asked on a future job interview, what's the difference? What's partial application and currying? The answer is both of them specialize.
Exactly.
They do it differently.
Both of them are specialized functions, specialized function techniques. So, but the first is preset some arguments now, and then receive the rest of in the next call. And the currying doesn't preset any argument, and it receives each argument at a time.
Application takes some input now, all the rest of the input later.
when you
Currying
can
takes
use that partial application, perhaps, for example, for uh, presets, right? So presetting values when you are going to run your application in a particular environment, that'd be a very good use case. So anytime that you call that function with these preset values or this partial application, you know what is going on behind the scenes. So say, hey, I want to run now this on Node, on Ruby, on Haskell, on PHP, in Python, Java.
It's no input now, each input one at a time. By the way, I want to back up real quick, one slide. Skipped over one thing I didn't want to skip over. There is this notion of what I would call strict versus loose currying. And I'm calling this out because you're going to encounter this and you may ask yourself. This idea that I've been showing you with currying has been like we see on line 7, which is that each time I call the function, I provide only one input. Because that's how we did it when we manually curried. That's how it works in Haskell. You provide one input at a time. I would call that the canonical or strict interpretation of currying. But if you had a function, say something that received 5 inputs, and you knew 3 of them right now, and you wanted to wait to define the other 2, you can see that it would be a little bit annoying to have to do 3 separate function calls with 3 separate parentheses. It might be much more convenient, like line 10, to just be able to provide 2 inputs all in one call. You see where I'm coming from? So that technique is what I would refer to as loose currying, meaning at each level of the function call, you can pass in 1 or more arguments. And the function that you get back is waiting for whatever the next argument should be. You with me? The reason why it's important to point out loose currying is because, as far as I'm aware, every JavaScript functional programming library that I have seen does loose currying, not strict currying. But if you're really trying to adhere to the true notion of what currying was as it was conceived in Haskell, you'd be doing strict currying. I think the reason why those libraries chose the loose currying form is for convenience only, not because it's the more canonically correct way of doing it. So just be aware when you see something like line 10 where multiple inputs are being passed, that still might be currying. It might just be loose currying instead.
Why does partial applications still exist in functional programming?
That's a good question. So the question is, why, if currying is generally preferred, and you will find that it usually is, why even have a partial application? The best answer I can give you, other than the fact that it's sort of historical, and once something is in the canonical body of work, it's never going to get removed. Other than that, I would say there are some cases where it would be more convenient to do partial application than currying. For example, let's say you have a function that starts out expecting 5 inputs, and you want to produce another function that expects 3 inputs. You want to preset only 2 of them. If you were to curry it, 2 things would be true. First of all, you'd have to call it twice, and that's a little annoying. But secondly, the function you'd get back would not be a function that was expecting 3 inputs. It would be a curried function of 3 more chains. And that might not be the shape of function that you want to pass around. So it might be the case that a partial application produces a more preferable shape. That's not going to be common, but that's why it might still exist, is that sometimes that tool might produce a function shape that is more preferable than a curried function.
More preferred here.
All right, remember the idea of, we did this add function before, and remember this idea of binary functions taking 2 inputs. What if I wanted to, say, do a map call? I know we haven't talked about map, but many of you are familiar with the idea of map, where it calls a function against several different values. If I wanted to add 1 to all of the values in my list, I could take this add 1 wrapper function and call it pre-specifying the number 1, line 4, pre-specifying the number 1 as one of the inputs to this general add utility. Why do I have to do it that way? Why couldn't I just pass add as my mapper function?
You're calling a function.
Because the so you're calling a function. Wait, what?
In my list, I could take this add 1 wrapper function and call it pre-specifying the number 1, line 4, pre-specifying the number 1 as one of the inputs to this general add utility. Why do I have to do it that way? Why couldn't I just pass add as my mapper function?
You're calling.
Because the shapes are different. Because the shape are
a
different.
function off of the array.
Right, map is going to take whatever function you provide to it, and it's going to call it with each value in the array. So it's going to call it, 5 times here. But why would it not be appropriate for me to pass add on line 3 instead of this
Because
function
of the
that I
shape
called
of
add
the
1? Why
function.
couldn't I just pass in add?
They have different arguments.
They have a different shape.
Different.
Do you see the shape? Add is a binary function. Mapper functions are expecting unary functions. A single value is getting passed in. It's the wrong shape. So what are we doing with add 1 here?
Well, returning the proper shape that it needs to, which is one argument.
Fundamentally, we're changing the shape, right? And how are we changing the shape? By specializing it, by pre-specifying one of the inputs. In this case, the first input to the number 1. So you can probably guess where I'm going with this. It might be better to have a curried version of add so that I can call line 10 add of 1 that makes my more specialized function that is the correct shape.
So it's because currying is now allow us to pass is the input anytime you call this function in one single input, right?
This is an
get it.
extremely common technique in functional programming. You will see this hundreds of times a day when you get into functional programming. Calling these little functions that are curried, providing one input, you get back a unary function and you pass that into like a mapper or a composition or anything like that. You will see this all over the place. So this is why currying ends up being the far more preferred form, because you could have done it with partial application, but it would have been a little bit more awkward here. It's nice if the add function is just automatically curried, and anywhere that I need to make the specialized function, I just call that with one input.
Where is the curry function defined?
It would be provided by a functional program.
by a
I'm
functional
not showing you the
library.
implementation of it. It's a little bit complex. I'm not showing the implementation of curry, but it would be a
So for example, if you take a look now at the curry here, you say curry partial application in Ramda. Yes, it is. Ramda documentation in curry. That's right. And then you say, hey, I'm going to curry is this function. So add 4 numbers, and then currying add 4 numbers. You're gonna pass the function, and you can see you pass is the more general function here. And here you can say, hey, I want to make is the partial application of this too. All right, and then I'm gonna pass the rest of the arguments. And on the last call, I'm gonna do is this. So why we are doing this? Because we might, for example, want to hold some values at some point, and then another one at some point, and then after that construct the entire computation, which is in this case 10. Really? It's a 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. Yep. Recurring, not working well with default parameters. Okay. Incurring n. Okay, all right.
functional programming libraries API. You'd call like ramda.curry or r.curry or whatever.
So what you're saying is that currying is often used to sometimes call a library that is already available for the programmer?
I would characterize it this way. So one use case for currying is that specialization. But another offshoot of the idea of specialization is that you're changing shape. And that means that in places where, for example, I have a binary function that I need a unary function, that a currying specialization is sometimes the right tool for that job. So currying allows you to take an existing function that has one shape
not only of the
and
value,
specialize
but
it, producing a new function that is more specialized with a different shape that has the shape that you want.
And this is when now composition kicks in.
All right, let's talk about composition.
The composition and immutability, recursion, and list operations from that. And then data structures operations, and then the async and line. Holy brownie. So that'll be all for this video. Take care. Bye-bye.